I'm going to tell you a little bit about comparative evaluation of life cycle impact of vanadium-based technologies to alternatives in structural steel and energy storage applications. So we've done a fair bit of work for Vanatech the last few years, working on coming up with a pretty big, pretty extensive life cycle impact across some of the major sectors. And this work seeks to take it in some new directions, and I'll talk about some of the motivations for this. What I thought I would do is really give you a very high level view of what we've done, and then we'll dive down into what we want to do. So of course, vanadium, we all understand is really a green metal. It is key to the energy transition. It's a critical material. It's deep decarbonization, and the energy transition depends on strategic minerals, critical minerals, depending, it's called different things in different countries. And vanadium chemistry is a very versatile, which enables lots of different technologies. And when we started this work about maybe 4 years ago, that's been a little bit 4 years ago, we wanted to have some benchmark assessments of critical minerals so that we could inform public policy. And I think we've had a fair bit of success with that. So this is work that David Santos and Pranav did. We worked through rebar, steel sections. We did a little bit of work on auto steel. That's a more complicated sector in VRFBs. And our primary goal was to quantify the benefits of vanadium in carbon savings, energy savings, and we more recently extended that to water savings as well. This is some work that Manish has been pioneering in terms of embodied water use. So just to give you an example of this is the first paper we published back in 2021, so a couple of years ago, where we put together this workflow. So we looked at primarily at rebar. We were able to do a bunch of structural modeling. We did machine learning, and we waded through a whole bunch of structural steel data, figured out expressions, kind of like what Kevin was showing with Godowski's expression. And then we took that, incorporated that into structural modeling, figured out how much weight savings we get from vanadium microalloying. And based on how much material savings we were able to get, we figured out the cost of carbon and energy for some structures, making again doing some models on simple houses and such, and what the costs of vanadium pentoxide extraction are. And this is going to be key. We're going to come back to this in a bit. And we were able to estimate the amount of emission savings and energy savings because of vanadium use in realistic structures, and we were able to scale that with worldwide, rebar production and some really great data we got from Sisri. So, for example, based on structural modeling that Manish's group did, about 61% savings in steel from when you use 500 megapascal vanadium microalloy steel as compared to 250 megapascal. And these savings in steel, so the fact that you're using less steel, potentially less concrete, and building reinforced concrete structures translates to a whole lot of savings in carbon emissions, right? So that was the overall idea, and we were able to, we had really good data from China and the EU, and we were able to come up with some metrics. And here's what that told us. This is the article that was published in Environmental Science. We were able to save 0.38%, 1.01%, 0.19% of total fossil fuel footprint from across the world, China and EU, respectively. Okay, so and in perspective, that's a whole lot of emissions that are saved. 300 million barrels of oil, right? Or savings from 30,000 wind turbines running for a year. 40 million tons of waste recycled instead of landfilled. So those are some perspective. So there's a really, really large impact from just a little bit of vanadium microalloying. So that's why we call it punching above its weight, right? We then had some beautiful data from history that we were able to look at as a function of time, starting from 2005 up until 2020. Just looking at how building code changes in China created an increase in the amount of vanadium used in rebar, and how through a series of policy changes that were implemented in China, you saw lower grade rebar, grade 2, being phased out almost entirely, and then you see this grade 3 and grade 4 start to really grow out. And then as that's happening, we're seeing massive vanadium consumption increases in China, and we were able to take all of that data and translate that to carbon savings. And so this is a really great case study for how a specific policy intervention, which was implemented after the Sichuan earthquake, or series of policy interventions, have massively led to really large increases in vanadium consumption. And a side benefit that's probably unanticipated at the time is that carbon emissions are hugely cut by increasing the rebar grade in alloyed steel in China. Okay, and that was 230 million metric tons of CO2. So those were some metrics we could come up with for China. That was published in Matter. And more recently, again, end of 2021, early 2022, we published this work on VRFBs. Again, VRFBs are still an emerging technology, but we could this is a bit more complicated in terms of what goes into the model. VRFBs are, on the one hand, they are extremely low carbon in terms of their operation, but their overall operations lower efficiency, as you know, as compared to lithium-ion batteries and such. So we compared different scenarios where we have no batteries at all, which is pretty common as compared to lithium-ion batteries, and we predicted that we could save again, if coupled to a wind source, for example, VRFBs can save 2.13 million metric tons over the 20-year lifetime. And when coupled to renewable energy technology, the carbon footprint of a VRFB is much lower. So again, avoided curtailment is very substantial for VRFBs, and we've looked at different scenarios. That was the third paper. Some more recent work Manish has done focuses on water use. So we can see that since construction consumes about 16% of global water use, we've been able to benchmark that, and we see very substantial savings for that arise in terms of reducing water consumption when you use higher grade alloys. And so this is what we've published so far. We have some additional work that is just coming very soon. That's going to focus more on projections for VRFBs going out into the next next 20 years or so, that guide how's prepared, and then thinking about how that's going to impact carbon emission savings, and where's all the vanadium going to come from. We've got a little bit of a supply chain angle to it. So that's an article that's in preparation. So what inspired this project is there's a couple of papers that came out that talked about ultra low niobium alloy steels for what they call commodity grade structural steels, right? And these are short articles. There's not a whole lot of samples studied, and one of them is a conference proceeding at HSLA. What the author has done, and of course this is from CBMM, or he's a consultant with CBMM, is done some work in calculating the global warming potential, the avoided global warming potential, and it's a very, very rudimentary, and I would say kind of a naive, maybe intentionally so, model where they've just substituted a couple of things and calculated carbon savings from niobium alloying. So this is a little bit of a mischaracterization. It's not a rigorous study at all, compared to what we've done we're very much up until ISO standards and such. And so there is some concern that these calculations really may start to undermine the work that we've done on vanadium and start to project something for niobium that is not really true. And I think there is some need to do some additional calculations to compare head-to-head niobium alloyed and vanadium alloyed steel. Again, Kevin showed some beautiful work showing this in one specific setting. And so what we want to do is build on our earlier work and then look at embodied energy, embodied carbon, and embodied water for different structural components, right? And so steel making, as you know, has different aspects to it. And when you are comparing niobium versus vanadium microalloying, we really want to compare the whole process, not just what the person did, where they just added in a little bit of they subtracted the cost of a little bit of steel and added in a very small amount of niobium. So what we want to do again is, this is our proposed work, is understand some sort of a rigorous market projection, understand the potential of growth for vanadium microalloy steel, compare what happens between the two of them, especially as you know, the processing temperatures are much lower for vanadium. And then there's a pretty strong sense that we have for now, and of course, a lot of this has to be worked out, that the environmental benefits of vanadium are much more than niobium in terms of lower cost for vanadium production. And so, yeah, global construction is going to be very large, and keeping in mind these different growth scenarios, we want to do some projections for what would be the impact of using vanadium versus niobium alloyed steel, both in steel frame structures and reinforced concrete structures. So comparing these two, and so there's a few specific things we want to compare, and so carbon emissions, embodied energy, embodied water for primary niobium production versus primary vanadium production, co-production, recycling. I think we have some numbers for co-production, recycling. Even for primary vanadium production, we are seeing some really big efforts to push these numbers down for vanadium production, and in a way that I don't think is possible for niobium. So I think we have some huge benefits in just what is the carbon cost for niobium production versus vanadium production. I think there's going to be some pretty large differentials here. And then reheat temperatures, processing times, global transportation costs. Again, that's something we want to include in our model. As you know, the vanadium supply chain is much more geographically dispersed as compared to the niobium chain. Coming up with materials criticality indices, which also is something that we want to reflect, because again, niobium versus vanadium, we've got a whole lot more diversity going on in the vanadium supply chain. And this is something that, of course, as you know, we are maintaining for Vanitec, trying to come up with a database, and I'm going to be pushing on that a little bit more at the Vanitec meeting in Paris, and then comparing rebar versus steel sections, so steel structures, reinforced concrete structures, and seismic performance is another advantage for vanadium. We're trying to see what would be the best metrics to capture that, and then recyclability, right? And of course, again, vanadium recycling is already quite mature, and niobium may not be quite at the same level. So trying to capture all of these benefits through some metrics. And right, so we're going to apply these input-output based life cycle data, look at embodied water, carbon benefits, and then consider production, right? So including comparison with niobium, and we're going to recompute these impact assessments for some very specific studies. So this is what we had done. Primary vanadium production was only 20%, a lot of steel slag production, and then production from petroleum products. So we're going to try to look at this and compare this to what happens with niobium. And our goal will be to have some peer-reviewed papers out there to release substantiate carbon savings and embodied energy savings, use advantages of vanadium structural steel, present a rigorously validated comparison to niobium microalloying, sort of apples to apples, where what are the costs of these alloying materials, and what are the processing costs, and then what are the global projections, and put together some articles on this, and we'll sort of also help Vanatech prepare a bunch of presentations on this, and what we would be helpful if anybody has data or sources for the niobium industry. That would be really helpful. Of course, it is a lot of the production data is controlled by one company, but if anybody can point us in the right direction as we get niobium emissions or niobium production data that'll help us come up with better numbers. And what would also be really helpful is if you all have can provide some guidance with specific examples, hot roll strip or something like that, where you have a vanadium microalloying process and an analogous, may not be exactly the same, but a niobium microalloying process that gets you to about the same strength profile, and then we can do a apples to apples comparison of reheat times, reheat temperatures, processing times, amounts added of niobium versus vanadium, and so on and so forth. And so this is our budget request. So we'll have Pranav is still around on campus, and then we'll have a PhD student work for 3 months, so about 26,000. Okay, Manish is here as well. Manish, you're here. Questions? Happy to take them.
Sarbaji, thank you very much for that. Obviously, it's good that you presented this to this group today. For any questions they have, I'm gonna want you to present that again in Paris too, if you don't mind.
Sure, at the MDC.
Yeah, the MDC meeting, yeah.
Yeah, sure, no problem. Yeah.
Cool. Thank you. They'll be the one making the decision on funding it, but it was good for you to present this here to these folks in case they have any questions or thoughts. So I'll turn it over to anyone else.
Just a sort of question for Kevin in relation to this. Are you still there, Kevin?
I think we lost Kevin.
Oh, right, okay. I'll follow it up later. But Kevin's done some, obviously, some direct comparisons between vanadium and niobium strip steel. So I'll try to chase Kevin down and see if he can get some more data, which might be helpful for this proposal. So
thanks, Dave. I think what Kevin was presenting was one of the few examples I've seen of very direct comparisons, because he's purposely doing exactly that, right? Comparing niobium and vanadium microalloy.
You have that previous paper that I think you, Lee, and Vanatech with a direct comparison as well. So
yeah, Dave. Yeah, no problem.
We'll see what else we can find for you.
And also Michael Kuczynski got a few papers, very good. I will send to you.
Yeah. So,
okay, that would be great.
Yeah, we will help you out there. Okay, well, I think we're about coming to the end of the meeting now. So thanks for that, Sabajit. As I say, we'll see you in a few weeks' time in Paris, I hope.
In Paris. All right, sounds good. Thank you. All right, thanks, John. See you soon.
Before I draw the meeting to a close, I'd just like to draw your attention on the agenda which we sent out earlier. There are a few. There's a list of Vanatech-related publications which may be of interest to you. If any of you haven't got those papers, just let me know and I can send them to you. Just a comment about the Vanadium Award as well. Some of you may know we have a Vanadium Award every year. It's not been decided yet. I think the judges have to make their comments by the 31st of March, so we don't have a winner yet, but we'll obviously let you know when it is. I think what we want to try to do this year, normally it's a steel-related award, but we're trying to broaden it out so that we have things like VRFBs as well. So, but for this year, it'll probably be a VRFB type winner. So that brings the meeting to a close. I'd like to thank you all for your participation, your presentations. We had some interesting comments. Again, you've got my contact details, so if you have any comments that you wish to make, please let me know. And I hope to see you again at the next meeting, which will probably be in September sometime. So I think that's all from me. John, have you got any final words you'd like to say?
No, just thank you all, and particularly thank you for those in the chat who were working with me on invoicing dates and whatnot. That was very helpful for me. So I appreciate everyone's time today and look forward to seeing you next time.
Okay, so thanks everyone, and we'll see you next time.
Okay, bye bye.
Goodbye then.